Hello, class. We are in week 8 of EEE 121, and for this session, we will discuss an introduction to nonlinear data structures and trees. Okay, so nonlinear data structures are those structures that store information or objects in some order or hierarchy. Now, this is in contrast with linear data structures, which you've learned last week. Uh, and because those linear data structures, they store the information in a sequential manner or a linear manner. So examples of linear data structures are arrays, stacks, queues, and even linked lists. Now, nonlinear data structures are more complex because the data that you store are arranged in some kind of order. And there are relationships there that you maintain between the elements. So examples of these are graphs or trees. There are pros and cons about using nonlinear data structures. Number one, they provide for more versatility because you can now model more complex systems. And secondly, you can have more efficient memory utilization. And in terms of our usual algorithms of inserting, deleting, and searching data, uh, these nonlinear data structures provide better performance. However, the challenge is that it's harder to implement. And when we want to traverse all the elements, it's not possible in one run. For example, in just one loop. So we have to do some kind of backtracking. Now, how do we assess the performance of nonlinear data structures? Uh, these are very similar to how we treat the performance of linear data structures. We look at time complexity in terms of search, insert, and delete, as well as space complexity, the amount of space that we need to store the elements or the values that we need to store. Okay, so let's go to trees. So a tree is an abstract data type that stores elements hierarchically. So as you can see, there's a tree structure, very much like yung tree in nature. But here you have a root, which is the source of all the other nodes under it. And under that root node, you have 0 or more subtrees, as represented here using triangles. So each triangle here is also a tree structure. Yeah, so that's a general definition of a tree. Okay. And there are terminologies here. And basically what it says is that the nodes in the tree have a parent-child relationship. Okay. So if the tree is non-empty, then there's a special node called the root node that has no parent. Okay. But it has nodes under it. And every node under that root will have a unique parent node. Okay, and every node with a parent W is a child of W. Okay, so if your parent is node W, then you are the child of node W. So that establishes the parent-child relationship. Now, if there are two or more nodes that are children of the same parent, then siblings. They're called siblings. So very much like a family tree. Okay. Um, and a node V is external if V has no children. If there are no child nodes, it is an external node. Another term for it is called a leaf node. Okay. And those nodes that are non-external, or meaning they have child nodes under them, they're called internal nodes. Okay. Some other form of definition here, ancestors and descendants. So a node is an ancestor of another node if there exists a path from that node to the other node. So meaning it exists in an upper level compared to the other node. And the other node is called the descendant. Okay. Um, We also say that the subtree of T rooted at node V is a tree consisting of all the descendants of V in the node in the tree T, including node V itself. So this is the formal definition of a subtree. Okay. Um, Strictly speaking, also a node is an ancestor and descendant of itself. Okay. However, when uh, we want to refer to two distinct nodes to differentiate it from the trivial case of just referring to just one node being an ancestor and descendant of itself, then we call it a proper ancestor and a proper descendant. So meaning we're referring to two different nodes. Okay. The degree of a node is the number of its child nodes. Okay, so nodes with a degree 0 of, by definition, are the leaf nodes or the external nodes. Otherwise, they are internal nodes. Okay? The depth of a node is the length of the unique path from the root node to that node. So that's the depth, meaning how far is it down from the root. And the depth of the root is always 0. Okay. Another definition related to how to characterize the the number of levels in the tree is called is height. So the height of a node is equal to the longest path from that node to a leaf node. Okay, it's so um, from that node there could be many paths to uh, the other leaf nodes. Okay, so you have to get the longest path, and that is the height of that node. Okay, so the height of a tree is equal to the height of the root node. So it's always equal to the maximum depth in the tree. So that will tell you how deep or how high the tree is. Okay, and a path is defined as a sequence of connected nodes. In this case, the path from node A to node M is AEM, and it's a unique path because by definition, a tree will not have any loops. Okay, so in short, there's a unique path from any one node to a given node. So from the root to all the other nodes, since all the paths are emanating from the root, there's only one path. Okay? So in this case, what is the height of this tree? So we look at the uh, maximum, okay, the maximum depth in the tree. So as you can see, this is the longest path from the root to the leaf node U. So the height is 1, 2, 3, 4, 5. Okay. Right. So here are looking at this tree, referring to this. These are the definitions based on what we discussed so far. So I'll leave it to you to check this out. Okay. Now, I just want to explain briefly yung applications ng tree data structure. So there are many ways in which the tree data structure is used in practice. Since it is used to model a parent-child relationship, so anything with a hierarchical data structure where you have a parent and some child nodes, then you can store it using a tree structure. So for example, like a folder structure in your computer, in directory structure from, for example, drive C, and then you have the main directories, and each directory has subdirectories and so on. Also, if you're storing information like XML or HTML, there are elements there where you can have nested information. Secondly, and I will discuss this later, yung binary search tree is one that allows a very fast search, insert, and delete operations on sorted data. Okay. Heap also we will discuss is another data structure based on the tree data structure. The B tree and B plus trees are used for databases, okay? When you want to store very efficient, in a very efficient way yung mga database information. Syntax tree, I will explain this example. KD tree, a trie, suffix tree, is useful in pattern matching, pattern searching. Spanning trees and shortest path trees, we will discuss this later in the course. Okay, so I just want to show you. Here's a file directory structure, and this one can be modeled as a tree. In fact, the root directory is called a root as well. So, okay, and then what we can say here is that, for example, if the directory doesn't have subdirectories, then they are leaf nodes or external nodes. However, if they have subdirectories under them, like this /usr, then this is considered internal nodes. Okay, so another example is a syntax tree, which is just a tree representation of a piece of code with a required syntax in your source code for a programming language. So for example, if it's something like Python, a programming language, and the Python compiler would like to check for the correctness of your syntax, then your code will be represented into a tree, a syntax tree, and check for the required elements. So for example here, this code is the Euclidean algorithm for calculating the greatest common factor of two integers, very well-known algorithm. And when you put this into a syntax tree, then you have this. There's a while loop here, and then a return. So they are on the same level. So while and return, right? And then under while, there's an if else. So under while you have to check for the condition, and that's what it's doing here. And in the body, you have a branch for the if and else body. Okay, but what I want to show you here is that in the while, and then there's a condition, there is an operator here because the operator is not equal to. Okay, so the syntax tree stores b and 0 here, variable b and a constant 0. So the compiler will check, okay, this is supposed to be a binary operator, so dapat I should see 2 operands. So if that's correct, it was parsed based on your code, then you have correct. Otherwise, you will have like a syntax error. So, and you do that for all the rest of the parts of the source code. Okay, so these are very good examples. All right, so this is all for now. We will discuss binary trees in the next video.